Once more into the deep dark forest of the stoichiometry problems. This time comes out of chapter 4, and it's going to have the solution stoichiometry twist to it. Kind of like this problem because it mixes together some equation writing and some good old-fashioned stoichiometry from chapter 3 with the solution stoichiometry from chapter 4. As always, when we are getting ready to do something like this, we want to think about something that'll center our mind and bring peace to our soul. And so, for just a second, let's look at a picture of a baby elephant playing with some ducks. There. Now that we're ready to go, let's take a quick look at the problem. Okay. There are the components to the thing here. We are told, first off, that we're going to write and balance the chemical equation. We are told that a solution of strontium hydroxide, there's something you don't run across all that often, the strontium hydroxide solution, okay, aqueous, is reacting with nitric acid. The first thing they want us to do is write and balance this particular equation. Here it is. Strontium hydroxide, a base, nitric acid, an acid. I wonder how we came up with that. But it's an acid. And so, as always, acids and bases are going to react to produce an ionic compound and water. And here the ionic compound is pretty clear. It's going to be strontium nitrate. Remembering the charge on nitrate, NO3 minus. The charge on strontium by its position in column 2 of the periodic table. We're going to make sure we write those formulas properly. This is strontium nitrate, SrNO3 subscript 2. And being a nitrate compound, it's going to dissolve readily, aqueous, and water. Okay? And so there are the two products. Now, there's the chemical equation. Of course, we're going to need to balance the thing, and I'm looking at the strontiums. They're in good shape. 1 nitrate, 2 nitrates, as I'm considering the ion together. And so if I have 2 nitric acids, they are balanced. Looking over here at the hydrogens in the water, I've got 2 hydrogens here, but I've got 2 more over here. I've got 4 hydrogens on the left, only 2 on the right. That's pretty easily corrected by putting a 2 there. Now let's hope the oxygens work out. 2 oxygens here that aren't part of the nitrate, 2 oxygens there. There it is, nicely balanced. Okay, so there's the balanced chemical equation. It's pretty straightforward acid-base type reaction. And now the gist of the question. We are told we have 15 grams of the strontium hydroxide dissolved in the solution, and it's reacting with 255 milliliters of a 0.20 molar solution of nitric acid. And the question asks us how much of the ionic compound, the strontium nitrate, we're going to make. How many grams of this can we make? Right off the bat, there's the classic setup of the stoichiometry problem. Balanced chemical equations, amounts of something, question about the amount of something else. We are also given very specific information about both reactants. Yes, this is a limiting reagent question, okay? And so we're going to start off with the pretty straightforward, simple one we ought to be able to get to pretty quickly, and that is how many grams of strontium nitrate can you make from 15 grams of strontium hydroxide in this particular chemical reaction? And so, pretty straightforward, away we go. 15 grams of strontium hydroxide. And grams, moles. We look up the molecular weight. 121.6 grams is 1 mole of strontium hydroxide. In our particular reaction, 1 mole of strontium hydroxide is equivalent to 1 mole of strontium nitrate. And then finally, the third step, 1 mole strontium nitrate has a molecular weight of 211.6 grams. Okay, strontium nitrate. So we start punching away on the calculator, and what we're going to come out with here is 26.1 grams of strontium nitrate. Okay, pretty straightforward there. But now we have to work on the second one here, because this one could be the limiting reagent, or it could be the strontium hydroxide. We don't know. And our strategy, the straightforward strategy, is to simply do the stoichiometry problem twice, turn this in the amount of product, turn that in the amount of product, and look for the one that produces the smallest amount of product. We've got the first half done. Now we have to work on the nitric acid. In chapter 3, we'd have talked about, we have, 2.5 grams of nitric acid or something like that. This time around, we have a solution. Now, sometimes students get confused as to what to do with a solution and that molarity there that's somewhat unfamiliar or a little bit questioning. At a lesser university, students would just say screw it and go on and do something else, but not here at Georgia Southern. No. We remember that the first step of all stoichiometry problems is not turn grams into moles, it's turn whatever you're given into moles. That's the critical thing. We are often given grams and we use molecular weight to get moles. We don't have to be. And this time around, we're not going to use a molecular weight. We are going to turn what we're given, 255 milliliters of nitric acid, into moles of nitric acid. And we're going to do that using the molarity, moles of nitric acid per liter of solution. Now, remember the definition of molarity. I am going to write it, I just said it, I'm going to write it out in grand detail, 0.20 moles of HNO3 in 1 liter of solution. It's a conversion factor between moles and liters. Oh, look, I have milliliters, which means I have 0.255 liters of my nitric acid solution. Okay? And if I want to turn whatever I'm given, like these liters, into moles, I know then liters must be the unit down here, moles must be the unit up here, and we are talking about nitric acid now. And by definition of molarity, it's 0.20 moles of nitric acid for every 1 liter. There. That is how I turn volume into moles. Because remember, the first step of a stoichiometry problem is turn whatever you're given into moles. Okay? You could use molecular weight with grams, use molarity with volumes. From here on out, the rest of the problem is actually absolutely what we are used to doing. We need to turn the moles of nitric acid into moles of the product we're after, strontium nitrate. And these are the coefficients. That's pretty straightforward. The molecular weight of strontium nitrate hasn't been changed since we used it last. And so we now start punching away on our calculator, and we get 5.4 grams of strontium nitrate. Okay, very different predictions here. We look at the two answers, and we choose the one that produces the smallest amount of product. There is how much strontium nitrate we're going to make in this reaction, and therefore nitric acid is our limiting reagent. Okay, pretty straightforward. And you notice the same, and one reason I liked this particular problem is it allows me to write both types of stoichiometry problems, one right over the other, so you see all the similarities between the two. Okay, and because this one, the logic of this one is exactly the same as that one. Okay, we just have to be a little more flexible in how we convert whatever we're given into moles. Now, the very last question is kind of an interesting one. Is this solution now acidic or basic when the reaction is done? Well, we've identified that this one is our limiting reagent right here. I'll just write limiting. And of course, this is the acid. Strontium hydroxide is the base. By definition of limiting reagent, kind of what it means when this reaction is done, all the nitric acid is gone. We've used it all up. Therefore, strontium hydroxide is our excess reagent. We have more of that floating around in the solution. That makes it basic. So at the end, the solution will be basic at the end of the reaction. Okay, so there. Pretty straightforward, really. This is the only real new thing in here, but the logic of it is exactly what we've learned before. So look that over, contemplate it for a bit, practice a few on your own, because of course, watching me do it is great. Doing it on your own is even better. And talk to you later.